Thank you. I had some internet issues, so part of this talk was planned to be a code demo, but I'm unlikely to be able to install random code onto this this laptop, so I can easily demo it to the people in the room. For the people online, it'll be trickier, but everything in this talk and the things I'll refer to are all available at a web page, which I'll link to. And so, yeah, I have been developing, go back, been developing this piece of software called HOGBEN for a while with a variety of different people, and I'm now at ESS, but most of the work I'm presenting here was done whilst I was at ISIS. So yeah, thought I'd quickly go through the concepts of what I was trying to do with an aside on training AI models, and then why, as a kind of side product of what I've been doing, it could be helpful for AI, but also everything else. Maybe we'll see. So this is a guy called Lancelot HOGBEN, who was the arch nemesis of Ronald Fisher, because all of my code uses the Fisher information. But he was the head of the Eugenics Society in the UK, and we were not a fan of this, but he did some good statistics as well. So, so we named it after his arch nemesis. So yeah, the concept is to try and run an experiment in a way which gets you the most information possible. So obviously you're trying to do your experiment, and it could be on lipids, solar cells, magnetic layers. It doesn't really matter. You have some information you're trying to extract, and it turns out that for a given instrument, how you run that instrument changes the amount of information you can extract about the things that you care about, and it changes it quite a lot. So one of the things that we can calculate is, for a specific instrument, what angle should you go to measure at, what water contrast should you use if you're using water contrasts, or how long you should spend at each one of those as a fraction of your time in order to get the most out of your experiment. And there's another part of it which I won't really go into, but quite often there are bits of your sample which you don't care about as much, let's say. So they're not scientifically interesting, but they're needed for your science to work. Quite often you'll have a substrate and you don't generally care what the substrate does. Sometimes there's buffer layers on the substrate. I've seen a lot of talks with gold with a thiol self-assembled monolayer to have a free-floating lipid bilayer. What thickness should you make that gold layer? Doesn't affect your lipid as long as you're not increasing the roughness. But actually, because your gold layer changes your entire reflectivity profile, the amount of information you can extract about your lipid depends quite strongly on how much gold you've put down. So if that sort of thing is potentially interesting for you, I won't talk about it too much here, but yeah, feel free to find me later. So I'm going to talk a lot about information. The important point is that information is exactly the same as error bars. So the information of a system is the inverse of your uncertainty about it. And this was kind of formalized mathematically by these guys, Kramer and Rao, who said that strictly that the variance in a parameter x, say your error bar, is always going to be greater than or equal to 1 over the Fisher information. So you can never have an error bar smaller than the inverse of the Fisher information. So this applies for a particular parameter. It could be a thickness or a density, but it also applies for all of the covariances between parameters. So just giving you a little picture here. If you have two parameters x and y, then you also have these this covariance x plus y and x minus y, and more generally you'll end up with something which looks a little bit like these matrices where you have a covariance matrix of all of your parameters, which tells you how correlated your parameters are to each other and how well each of the parameters is determined by itself. And so for every covariance matrix, you can have the information matrix. So this is obviously a toy example, but yeah, the numbers generally don't mean anything, but the ratios of numbers to different numbers are the important thing. So yeah, how do we actually calculate this Fisher information? Because it seems like if we have this Fisher information, we know the best that we can do from our experiment. So what we want is the parameter values of our model, as well as the variances and covariances between them. But what we actually measure is neutron counts at a given angle and wavelength. It's important that we don't measure Q, we measure counts at a wavelength and angle. And what we generally know is that we have a rough idea of what we're measuring. Like we have a model of our system, and that shouldn't be, generally speaking, too far wrong. And so with our model, together with the count information, that's everything you need to calculate the Fisher information. And once you've got the Fisher information, you can transform that into parameter space and then give yourself a lower bound on all of these parameter variances and covariances. And this is exceptionally fast, because all you're using is the number of counts and a model which you do some calculations on. But people like the people in the other session are all working very hard to make those calculations as fast as possible, so it's quite easy. So all you need to know effectively is if you have an idea of what you're going to measure, a model, you have that before the experiment. You also know which instrument you're going to measure on, so you can get or ask nicely the instrument scientist, and they'll give you how many neutrons will you get per wavelength per time period, and then actually before you've even done the experiment, you can work out what your error bars will be after a certain counting time, or the best that they could be, or the errors on your parameters will be, which is actually what you care about. And you can also do things like changing the model, so changing the sample that you're going to measure to see if you could have done better. Change the gold thickness to see if you know more about your lipid bilayer. So this is cool, but the way that we would do this is to simulate the experiment. And so this is kind of...
Just one sec, Josh, in the Zoom, they still see the first slide. Or I'm in Zoom, I only see the first slide.
Interesting.
Yeah. Now it's the speakers, they need to swap the view.
Maybe.
Yeah, perfect.
Yeah.
Okay, thank you.
Okay.
Sorry.
Okay, so you start with the two things that you know. So this is the pulling it counts per second. Doesn't really matter what time or thing you're using. ISIS, it makes more sense to do it in terms of a microamp hour, like number of protons illuminating your target. Against wavelength. So you also have the information that you're going to be measuring your sample at a specific angle. I should also say that this is all for time of flight, because that's what I've been focused on. For monochromatic, the principle works as well. It's just not as streamlined in the code. So you then multiply this by your model, which you can generate. The way we've done everything, we've tied everything quite rigidly to RefNX because I'm not a good enough software developer to not do that. There's a nice API, so I decided to use it. And then what you get is a number of counts as a function of Q. So this is the kind of expected number of counts you get. But what we want is an experimental, like a real looking experimental data set. So you don't want the expected value. You want kind of what you would measure. So for each one of these data points, you generate a +1 distribution. And these are what the +1 distributions look like for different values. So for one count, this is the like an expectation value of one count. You get a distribution which goes something like this. You can't see that. Oh, it comes over here.
Yeah, lambda is counts on the way.
So yeah, lambda here is counts.
Oh, okay.
Sorry, yes, good point. This is where maths terminology and neutron terminology provided. Yeah, and so we take these +1 distributions and then we sample from them. Take a piece of sushi, and that will be somewhere around the expectation value, but it won't be exactly it. And that will give you effectively like this realistically noisy counts versus Q, which you then just transform back to reflectivity, and your error bar is the square root of the number of counts that you've got at that point. And it turns out that this approach works very well. What's going on?
No, it's
Okay. Yeah, so on the left here, you have a graph of, it was a very nice sample I had. It was some copper and some silicon grown on some quartz, very flat and very homogeneous. And I measured it at a lot of different angles. And then I did a very good fit, and then took that model and then tried to work out, okay, here's a random sample of what I should have measured. And I can't find a way of telling that these two are different other than at this point, I messed up in the actual experiment. So there's a couple of data points that are dropped off, which I should have chopped off in the data reduction, but didn't. Yeah, so kind of an aside, if anyone in the audience knows of a good way of testing if two data sets which have error bars associated with each point are the same, I would very much like to know.
I think that's impossible. You can't demonstrate it as the same.
Okay, but if
boundary of how different they are.
If you can get a number for how likely it is that they come from the same distribution, a sample from the same underlying distribution, let's say. Anyway,
Ask somebody with superior knowledge.
So hopefully this shows that I can simulate an experiment and it looks like it would do on the beamline that I'm going to measure it at. And just kind of I did this as a thing for fun. How fast can you measure? Can you calculate these things? So Andrew Nelson has made a nice comparison of all of the different calculation engines, and generally you can calculate one key point model in a microsecond. You can sample from a +1 distribution with NumPy, one sample per 10th of a microsecond. So for each one of those key points, we need to sample from a +1 distribution. And array multiplications are absurdly fast in NumPy. The only numbers I could find, I couldn't believe, so I didn't put any here, but essentially it's 0. So let's say the schema in principle has the ability to be exceptionally fast to simulate very realistic data, and it's currently 1 millisecond per data set. So yeah, why is this useful for training AI models? Well, I think most AI models, even small ones, have huge numbers of parameters to be trained, and I can't remember in which talk it was, but someone was mentioning even trillions of data sets for training things, which yeah, is pretty ridiculous. As well as that, so that's for kind of traditional supervised learning, where you input the data with some known parameters and then you train your model. There are other techniques called unsupervised learning, where you don't require as much data, but it's still, you want to test them and you want to be able to kind of benchmark these things with a known ground truth. And as we've seen, yeah, real data is pretty scarce. And even if you have real data, how confident are you that the analyzed parameters from that real data are good enough to be able to say, yeah, this is the right thing? So even the data sets that do exist, there's probably 1 million times less than there need to be, and you can't be that certain. So yeah, the ability to make nice, realistic data, I'm proposing HOGBEN to be one of the solutions for. Now, I was going to go for a live demo at this point, but I will skip that temporarily and finish the talk and just mention that there are a few drawbacks to this approach. So when you're creating your model, you're limited by your imagination, essentially. So you can make a sample structure, but you don't know that it will be what you're going to measure, and you don't know that you can't generalize a particular sample structure to one which is parameterized in a completely different way. Like a magnetic multilayer will never be a lipid bilayer. And yeah, I've mentioned magnetism, but actually within my code, I haven't really done much with magnetism because it was a bit tricky in RepNX, and supporting another code base which was able to do magnetism was beyond my abilities. So yeah, you'd need to define a new model type for every kind of idea for a model structure. But once you've done that, you can randomize very easily things like layer thicknesses, SLDs, roughnesses, but you can't randomize reparameterizations of structures, which is quite often a thing which people want to do. So yeah, to kind of conclude that, yeah, HOGBEN is very good for planning an experiment and hopefully optimizing how much information you can get. I did some experimental validation of this approach and found that, yeah, you can get upwards of twice the amount of information, so half the error bar size, not the error bar, because the error bar is the standard deviation, not the variance. Effectively, twice the neutron flux just by changing how you do the same experiment on an instrument. And yeah, I haven't even tried to optimize for speed. A millisecond per data set is maybe not quite fast enough, but there's the ability to go a lot faster. So maybe you can generate data on the fly when you're training your AI models. And so yeah, I thought of a couple of questions maybe to prompt discussion. I know Max has some more which I haven't added to this, but yeah, for if something like this is accepted as this will generate the data that you will get, then maybe it's better to have like a database of sample structures, like of ideas, rather than the data sets, because then you you have the ground truth associated whenever you're generating these things on the fly. And yeah, obviously you do eventually want to check things against real data. There's the question of whether or not the databases which should be continuing to develop to create this, like it's going to take a while. Maybe in the meantime we can augment these with this simulated data. So this talk and the Jupyter notebook, which I can either go through or not, are all available at this page. So yeah, please feel free to get it. And the notebook has essentially it's two different models where you are able to generate, you know, I think it was 10,000 data sets in 16 seconds, all of which were randomized thicknesses, roughnesses, SLDs for a simple layer and for a lipid. Yeah, the model complexity doesn't affect the speed